So this is going to be a two-man show. Marco from Resultech and myself from Ultrasoc. We're going to talk a little bit about how RISC-V can be used in ISO 26262 type environments. So loose agenda is as follows. So I'm going to tell you a little bit about Ultrasoc now, and then so Ultrasoc has a number of customers that provide silicon IP, which our customers use, which is the upper half of that diagram. The reason for showing this is that the IP that we use is used in various different kinds of applications. It's not just one target market. We have customers in the SSD, right to automotive, AI, and servers. But the IP that we provide can be used in lots of different ways. So we provide IP that can be used for analytics. It's on-chip analytics. It's done in hardware. We also support debug of the underlying SoC. It's been used by several customers as we speak. Originally founded in 2009, and we have about 30 employees based out of Cambridge, UK, and a little bit more. We've been foundation members of the RISC-V since 2016, and we're chair of the processor trace group. We've been contributor and member of the debug group, and our partners with RISC-V are the likes of Andes, Esperanto, Lauterbach, and Microchip and Sci-Fi.
Resultech is an Italian company born in late 2007, headquartered in Pontedera, near Pisa. We provide engineering consulting and design services to companies and public bodies, mainly for resilient system and infrastructure. Our main domain of application is railway, automotive, and industrial. We also regularly join international research group on ICT topics. We are a member of the Italian Mirror Group for ISO26262 road vehicle functional safety, and also for ISO21448, which is the safety of the intended functionality, or SOTIF, which is, was born to support autonomous vehicle. We have customers mainly based in Europe, but also on the Far East, like Japan, and on the West, like in the United States. What we do? We design safe systems and system ownership safety libraries. We perform verification, validation, and safety assessment on hardware and software at different levels, and we also provide support towards certification. Additionally, we perform security assessment, and we offer training courses tailored on specific customer needs.
If you came here to become ISO 26262 experts, that's not going to happen. What I'm going to talk about, just give you a high-level view of what it might encompass. So it's an automotive specification adaptation of IEC 6010508. That's a bit of a mouthful. It provides an automotive safety cycle from management through development, production, operation, service, and decommissioning. It defines the functional safety aspects of the development process, so requirements capture, design, implementation, integration, validation, and configuration. It then outlines an automotive-specific structure of risk classes, known as ASILs, automotive safety integrity levels. Most of you probably heard of things like ASIL A, ASIL B, ASIL D. So ASIL D being the highest category. This specifies the requirements for validation and confirmation measurements to ensure sufficient and acceptable levels of safety is being achieved. So for autonomous vehicle technology, a new generation of robots and medical systems, we're seeing an explosion in the development of cyber-physical systems. And these systems, the common theme here, use advanced software to interact with the physical world. And this means the safety is of paramount importance. The ISO26262 framework, let's stop saying that, my tongue's getting twisted. The framework adopted by the automotive industry plays a key role in assuring the implementers and the users of the road vehicles are safe. In particular, the software complexity is increasing, and it will continue to do so. So reliable and safe execution, even in the presence of transient faults, is key. So in line with the 26262 requirements, it's important to do proper verification and validation. It's essential to have runtime protection for hardware failures and software failures. From a system perspective, both cases lead to the deviation of expected system behavior. So non and low intrusive and high efficient control of software execution flow is needed. CPU's cores, that seems to be the flavor of the month, need ISO 26262 friendly hooks to implement runtime protection. This could take the form of lockstep or redundancy support, deadlock detection, error detection, pick your favorite variety, ECC, parity, and so on, hardware stack protection, memory protection. The key requirements are non-intrusive is preferable, but otherwise low intrusive is acceptable. Needs to be a small impact on silicon area is acceptable, but it should have negative impact on software performance. Okay, so just lead you into what the UltraSoC technology is before we go to how this can be used to help with 262 systems. So typical SoC have a bunch of blocks hanging off an interconnect, and there's going to be heterogeneous cores, not just one flavor of cores, and you may even have a RISC-V in this. DRAM controllers and other peripherals, all tied together via an interconnect. There's the classic run control system that people need. The run control is talked to via our message engines, and then there's I/O to the outside world. So that is processor-centric debug, so that's intrusive. What else UltraSoC provides is monitors that help observability of the interconnect. These are runtime configurable, so these are protocol aware and transaction aware. With that in mind, you can use that for observing conditions on the interconnect and help with functional safety. We have ways of other communicators. These are things that talk the UltraSoC world to another world. In some cases, you want higher bandwidth than the JTAG, so we have those. We have a unique USB 2 communicator, which is done completely hardware. There's no software involved in doing that. So from cycle 0, you're up and running, and you can start observing the system. You have a way of pouring data into memory for systems where there isn't high bandwidth off chip, but you can then go and pull it off later. And then we have a bunch of other blocks, things like the status monitor, which is an embedded logic analyzer to observe usually custom signals or internals of a CPU. And then we have things like the static instrumentation, which allows for code that's instrumented to posted writes, or indeed hardware. So what happens with it, in the case here, if you ignore the run control aspects, the rest of the system is observing the target system without the target system knowing that we're there. And we're observing it in a non-intrusive manner. And we can use that to help with the functional safety aspects.
To approach the problem from a functional safety point of view, we'll start from the concept of an anomaly. Anomaly in a dataset is something which doesn't fit in. Here we have some example of anomaly. We have a point which is a single data instance not complying with the usual trend, a contextual anomaly, which is a single data instance, again, unexpected but in a given context, and then a collective anomaly, which is a collection of related data instances that is anomalous with respect to the entire data set. Anomalies can be caused by hardware permanent fault, but also by transient fault, which are tough to be detected at runtime with simple and non-intrusive safety mechanisms. But moreover, they can be also caused by malicious faults. It means that an anomaly detector may be also a powerful tool to detect security violation. The concept of anomaly is also useful for resolve static issues. In fact, an unexpected scenario acquired by a sensor may be seen as an anomaly. Why anomalies are important? Anomalies are important because they can reveal in advance errors and failure in the system. So they can be exploited also in modern automotive systems to detect system failures. Here we have the fault propagation chain, which shows causal relation between fault and failure. At system level, a fault, when activated, will become an error. Then the error propagation will lead to a failure. If this failure is not detected within the fault-tolerant time interval, this can cause an hazardous event, which in a worst-case scenario can lead to an accident. Breaking fault propagation chain, we did the FTTI. If TTI is a time which range in the order of 100 milliseconds, even less, is a key for functional safety. So lower level component anomalies, lower level component failures can cause anomalies at the system interfaces much before than the actual system failure. So knowing where to look at, we can build an anomaly detector which can be used to prevent system failures. How to do this? First of all, we need to observe the system, which means defining a monitoring strategy based on specific needs, which may be functional safety needs, but also security needs or performance needs. Then we have to understand where to look at. It means that we need to define static rules derived from system invariance. And then we have to take the advantage from architectural features, those functional safety hooks we've spoken before. Then we need to instrument the software. So the software instrumentation has to be applied with minimum or better non-intrusiveness. And ideally, the software instrumentation can be elaborated automatically from the software application load. Concerning the monitoring software, the best option would be to run it on a separated processing unit in order to have low impact on user software execution. But this is not mandatory. What is really essential is the presence of the hardware infrastructures.
We're here because it's RISC-V. So one of the concerns have been that RISC-V is immature and therefore not usable in high integrity systems. However, with the right infrastructure in place, we don't see this being a problem. As my colleague Marco said, if we go for an approach where you have, in this case, the system CPU is actually running the application in the SoC, and then we have an analytics subsystem which is there taking the data from the various monitoring blocks. So in this case, we have the AXI bus monitors, which we mentioned earlier. They're the protocol-aware monitors. We have the static instrumentation block tied together with our message passing infrastructure, which isn't going to affect the behavior of the target system because it's not using its interconnect. And then we have a way of getting data in and out of the system. But more importantly, the data that's been collected by observing the behavior of the application on the system's CPU is then sent to the analysis CPU.
Here we are showing two examples. The first one using the software and the hardware architecture to detect anomalies. So here we have a control flow monitoring example. We have on the left-hand side the assistant CPU running an application software, and then the analysis CPU running the control flow algorithm. The application software has been instrumented in a way that the CPU gets hardware messages when the software reaches given waypoint. In this way, the control flow algorithm can checks for valid path. So in the example here, we see that the application software, maybe due to a failure, ran from B1 to A1 to B2 to A4 and then to A6. This path will be detected as a not allowed path, and an alert will be raised by the analysis CPU to the system CPU. Second example is based on error counter in data acquisition loop. So here we have again on the left-hand side the application software implementing an acquisition loop. On the right-hand side, the analysis CPU running the monitoring software. In the middle, the AXI bus monitor, which are observing the bus. So considering P1 as an input source, for example, a camera or a radar, a LiDAR, or whatever, if in the checkpoint C1 the acquired data validity is performed, then if the data validity control fails, an handler routine is triggered on the bus. The AXI monitor is observing the bus, so it's aware of each handler routine which is triggered. And then it can also pre-filter events. So if some such events will happen with a frequency lower than a given threshold, this event will be filtered away. And then there is a threshold-based check on each handler routine. If in the overall handler routine we have a number of violations greater than a given threshold in a specific time windows, the analysis CPU will trigger an alert. This can also be done instrumentally in the software, but in this way we introduce a certain degree of intrusiveness. Then it can affect system performance, which are keys, especially in the field of autonomous vehicle. And then it brings to a poor maintainability, because once you need to change the observation point, you need to rework on the whole software, application software.
So the key characteristics to consider for in-life safety and security cases are non-intrusiveness, the ability to monitor and detect after you've observed some anomaly, raise an alarm without disturbing the operation of the SoC. How that alarm is handled is usually a system-dependent thing. We need to be able to react, or i.e. detect, in a timely manner. So, you know, if you're driving in a car and you don't react in a timely manner, you probably knocked somebody or crashed into the wall or knocked somebody over. So the monitor's operating hardware rather than software will alert in microseconds rather than hundreds of milliseconds. And with such an infrastructure in place, there is no barrier to RISC-V being deployed in high integrity systems. Thank you. That's it.
So from what I understand, you have a separate CPU that monitors the main CPU. So your main CPU is generating all these counters, all this error conditions, and then there's a separate CPU that actually comes in and looks at those and determines whether or not there's a fault.
So that's this is an example of how you can use the non-intrusive monitors to do that. Yeah. So as Marco says, you could feed that into the application software running on the one CPU if you wanted to, but you know you could have a very small analytic CPU on chip to do take the data from the monitoring infrastructure to do that.
Okay, and what kind of responsiveness would you get from that? 100 milliseconds, tens of microseconds?
Microseconds. And so you're doing the metrics generation, as Marco pointed out, if the filtering that the bus monitor will do, that will be in nanoseconds.
Thank you.